is Causal Inference and Statistics, and we are the last chapter, chapter 4, and we're on question 4.3.2. I think that this might be kind of a long video because part C, I think, is a little bit confusing and difficult, and it has taken me a while to figure out how to do it. So, but we'll start here with part A. So here in part A, we're supposed to, well, let me just scroll down to the answer. Okay, so we're looking at this DAG from figure 4.1 in the book, and we're supposed to describe how the parameters A, B, so here's A, B, and C, can be estimated from non-experimental data. In other words, from observational data. Okay, and so I mean, roughly what we do. So first we'll tackle A here. Well, we notice that A is the causal link between X and H, and so we can just regress H on X plus its own little error term here, and so that's going to be beta XH times X. Okay. Well, now the A here is the beta XH. Okay, right, because it's the link from X to H. So good enough. And then for B and C, we can do the same thing, but now we're regressing Y on X and H. Okay, so we get C because C is the beta coefficient between H and Y. Right, so we get C there, and then B is this link right here, and it's the beta coefficient for beta XY. Right, so that's B. And notice that we don't have to worry when we use this regression. We don't have to worry about the other path between X and Y that goes XHY, because by conditioning on H, we're blocking that we're blocking that secondary path for X. Okay. So now we're in part B. So in the model in figure 4.3, which I've reproduced right here, find the effect of education, which must be X, which must be college, on those students whose salary is 1. Okay, and so we're supposed to use Theorem 4.3.2 to compute this. Okay, so if you go to in fact, here, let me look it up off screen here. But Theorem 4.3.2 gives you an expression for it gives you an expression for the not the ETT, but for the expected value of a counterfactual. Okay, and so here we're just going to blindly apply that. Okay, but roughly what we're being asked to do is we're being asked to find all individuals for whom y equals 1. Okay, this and so this is the abduction stage if you're following by the rules in the book. Okay, and then with those individuals, we then regress X on Y and replace the random value of X with 1 and 0, and then we subtract them, right? So, and Theorem 4.3.2 gives us that we could use this expression right here, okay, or a version of it, okay, in which case we come out with tau, where tau is is just a beta coefficient for X in the regression of Y do X. Okay, that's what it comes out to. All right. So I think that these two are fairly straightforward. But now we get into part C, and now we're supposed to estimate the effect of treatment in the treated for a slightly different model. And the new model, instead of this right here, where we have X leads to H leads to Y, what we have is that h is affecting x, so this arrow right here gets flipped around. And also there is an interaction term which is not easily displayed in a DAG like this. Okay, so let's kind of make this a little bit more concrete. So our model, so our DAG now looks like this roughly. I don't have the A, B, C in there, but and because we've flipped the direction of the XH arrow, now H is just U of H, and X is a function of H now, and now Y has a interaction term here, delta, which is the coefficient XH, right? So there's an interaction between X and H. In other words, the effect of H depends on the level of H, or stated equivalently but oppositely, the effect of H depends on the level of X. Okay. So also the book doesn't really say whether the counterfactual should be based on X or H, and so we're going to do both. It's probably X, but that's fine. Now, the book does not really give very clear instructions, or at least I didn't think it gave very clear instructions on how to deal with this interaction term here. And so the first thing that I tried to do was just to try to apply this formula right here, okay, which is, kind of what I'm led to believe the book is telling us to do. And so let's go through that, and we're going to realize that it's wrong, okay? So here's the expression that I thought we were supposed to use, where tau is this expression right here, okay? Right, so we have the counterfactual value of y x1, y x0, okay? And we're just going to churn through all of this. So let's just find each of these terms. So the expected value of y given x equals 1. Okay, well, what's y? Well, y is just this, and everywhere where there would be an x, I just put a 1. So there's a bx, and so that's just a b. And then there's a dxh, and so there's a 1 there, right? So on and so forth. And so then we can simplify that, and we come out with this. And so now we have this thing right here, which is the expected value of h given x equals 1. Okay, so the way that I can do that is if I regress I regress h on x, then I would have, then the value of h would be beta xh times x, okay? Well, so now I need to find what beta xh is. Well, the formula for a beta coefficient is the covariance of the two terms you're trying to relate divided by the variance of, one of the terms, x in this case. And then, you just go through and you expand everything, right? So x, remember, is xh plus u of x. Okay, and so that's the covariance of those two. Remember, h is just u of h. Okay, and so then I take the covariance of this with u of h, of u of x with u of h, and at the same time I'm doing something in the denominator here. Instead of h, I'm using the variance of the linear formula for, or the variance of x, I'm using the formula for x. Okay, and we just expand. If these rules for covariance and variance algebra just isn't familiar, you may want to look that up. I don't think this is the right time for me to go into that. But in the end, what you come out with is that the expected value for h given x equals 1 is this right here. Okay. So if I plug that back into my expression up here, I get the expected value of y for x equals 1 is this guy right here. Okay, that's fine. And now the next thing that we need is this tau. Okay, so tau is just the expected value of y given do x equals 1, and then minus, same thing, but now we're doing do x equals 0. And you can just see that I'm expanding all of that out. Okay, and I get b. Okay. And then I think finally we need the expected value of x given x equals 1. Well, of course, that's just 1, right? The expected value of x given x equals 1 is 1. Okay. So now we put all that together and we come out with this right here. We get b. All right. Well, this is probably wrong, and there's a couple reasons we might guess that this is wrong. One is the book on page 107 explains that the actual answer should be this. Okay, but we're not getting that. We're just getting b. Okay, and maybe tau is b like it was above. But anyway, but obviously we're not getting this here. Okay, so so doing it this way, again, the way that I think that the book would suggest that you do this is not correct. I don't think that I don't think that the book is wrong. I think that maybe this part was written in a way that was kind of misleading. Okay, so this left me with the option of trying to come up with my own expression for this. Okay, so that's what we're going to do here, and this comes out correctly. And in doing this, I kind of had to, I don't want to say invent some operators, but operationalize some of the notation that is given in the book. Okay, so the ETT I can write like this most generally. Okay, the expected value of y given x is some set value x prime 2, given the evidence z equals little z, where that can be any set of variables and given values. Okay, minus basically the same thing, but now x prime is a different value for x prime. Okay, so notice that little z here is meant to denote the evidence, whereas in the book I think they use an e, but e is sometimes maybe confused with the constant, the mathematical constant e, and so okay. So so we're just going to expand one of these terms, right? These two terms are basically the same except for what x is set to. So we'll just expand a generic term. Okay. So I'm just expanding one of these terms. I'm using shorthand notation here, right? So so I'm going to take the expected value of y, but I have the expanded value of y, and here is where I am operationalizing some of the notation. I am making this little guy an operator, and you'll see how that how that little subscript operates. Okay, so I have the expected value of y for a particular value of x given the evidence. Okay. And so now I'm just going to break this into chunks. So the expectation operator is linear, so I can just take all of this. I can take this operator and just apply it to each one of these terms. So now I have the expected value of bx, and I'm continuing to carry this operator right here, this x prime operator, and I'm just applying that to each one of these chunks. Okay. And let's see the next thing I do. Okay, so the coefficients b, c, d, these are all constant. Okay, and so these values can just be placed outside of the expectation. So that's all that's happening there. All right. And so now we get to apply this little operator right here. Okay, so the way that this operator I imagine works is it says look to the left of me of whatever term I'm attached to, and if you see my variable, assign that to me, right? So here I have big X of little x prime, and so I just simply assign big X little x prime. Okay, and now here notice I'm going to use that same operator. I have big H little x prime, and so little x prime goes through and looks through the terms that it's attached to, doesn't see any capital X's, and so it doesn't do anything. So big H of little x prime is just simply big H. Okay, so I hope you see how that operator works, right? So now we're going to apply it here, right? So I have xh little x prime, and so the little x prime goes through and it looks for x's. So it sees the h and it doesn't change the h, but it sees the x and it changes it to x prime. Okay, so you see how all of that works. And then finally here for the error term, I don't see a capital X, and so in fact you know what, already this should be u of y. Yeah, I'm going to change that real quick. Give me just a second. Okay, so now I'm going to continue to simplify these terms here. Okay, so I have beta x prime given z, given the evidence, but the way that these set values work is it doesn't matter what the evidence is. It is just x prime. Okay, x prime cannot be changed by the evidence because we're setting that value there. Okay, and now I have c times the expected value of h given z. Well, the expected value of h given z means I'm going to regress h on z, so I'm going to have beta zh times z, right? Right. That's just what h equals, right? Now I have so now I'm going to take this guy. So again, I see this. So I have expected value of h given z. So I'm going to take the x prime and I'm going to take it out of all of that, right? Because the expected value of an established value is just a constant, so it can come out of the expectation operator. And then the expected value of h given z is again beta zh times z. And then I have my error term here given z. Okay. And so now I'm just continuing to simplify. So I have beta x prime, and notice that I have the same expression here and here, so I can combine the c plus d prime, dx prime, so on and so forth. And it turns out that this guy right here, we already solved this. We already solved this when x equals 1. Yeah, I think this might, sorry if this is a little bit confusing. Remember, z is x equals 1 here. I'm trying to make it kind of generic, but we already solved that up here, right? We already found expected value of h when x equals 1. Okay, so that's what we have. And so now I have an expression for these two generic terms, and so I'm just going to plug in the values that I know are there for this and for this, right? So remember, so this counterfactual term is this, which we found above, and so I'm going to have x prime 2, and I'm going to subtract, the same expression where I'm using x prime 1, and so when I subtract those, this part I think you can do for yourself, but when you subtract those, you eventually come out with this expression right here. Okay? So if I put in the values that I know exist, where x prime 2 is 1, x prime 1 is 0, and z is x equals 1, okay? All right, well, so anywhere where I see a z, I can just put a 1, okay? So there's a z, that's a 1. Anywhere where I see an x prime 2, I can put a 1, and anywhere where I see an x prime 1, I put a 0. Okay, we simplify all that, and we get this, which is exactly what we were meant to show in the first place. Okay, so there we go. Okay, so it turns out that tau is equal to b, and we actually already know that from some work that we did, some work that we did above here. Okay, so we already know that tau is b. Okay, so hope you're following so far. So there's our expression for ETT, and now we should be able to confirm this by running a simulation, okay, where we go through the steps of counterfactuals as presented in the book. So first I'm just generating some data here, okay, and so first thing I'm just going to get the hard values for ETT as we've derived it algebraically, okay, and it comes out to 3.4. And now we'll use the steps presented in the book. We're going to use abduction, action, and then prediction. So first I'm taking, so the observations for which the evidence applies, x equals 1, I'm taking those random components, okay, so that's abduction. For action, I replace any x with a particular value of x prime, and I have two x prime values here, right, 0 and 1. Okay. And then I just simply build up my expressions for y and for y with the particular x prime values and the evidence. Okay. So I can kind of let you walk through that yourself, but ultimately what we come out with when we subtract y given x2 and y x1, these two counterfactual values, we get 3.4 right here, which is what we found with the hard-coded values. Okay, great. Now, because like I said, the book's not clear whether or not the counterfactual in the question means that x is changing or h is changing. I've also done it here for h, and this video is getting long, so I don't think I'll spend as much time on it. But But again, I have first I need to derive the expression for the counterfactual values. Okay, so I have all of this, and I break I break each one of these terms down according to the conditional expectation and the counterfactual value. Okay, so we get all of that, right? And then I take I take my constants outside of the expectations, and now I'm going to apply the little h prime operator here, right? So x little h prime is just x, right? Because again, little h prime goes through its term and looks for capital H's and doesn't find any, and therefore it doesn't mean anything. Okay, same thing with here, right? So now it goes through and looks for capital H's, and it finds one, and it turns it to h prime. And here it finds capital H here. So we have h prime. Okay. This h prime doesn't affect that x. Okay, so we get all this. All right. So on and so forth. And now finding the ETT is just subtracting one counterfactual value from the other. And when we do that, we come out with this expression right here. So if we take, if we're applying our evidence where z is x equals 1, h prime 2 is 1, h prime 1 is 0, and we just plug those into the expression, right? So now this this value right here becomes expected value of x given x equals 1, and that just equals 1. And we have h prime 2 minus h prime 1, which is just 1 minus 0, which is just 1, and so we get c plus d. And so we can, so again, just for sake of simulation, or for a little bit more confidence in what we've done, we have the we have the algebraic derivation should come out to 5.5, and then we go through the same steps as we did above. We abduce, we apply the action, we predict, and then we look for the ETT, and again we get 5.5. Okay, okay, we'll call that good.